even more specific.
Two, four, six, eight, 16. You made it. That's impressive. Okay, welcome back. We're over halfway. You guys have done half the homework, half the quizzes. Okay, so essentially 25% of your final grade has already been spoken for, right? Half the quizzes you took. Each quiz is worth 5%. Homeworks are what? Do 30 or 30%? So, yeah, 30%. So 3% apiece or 15%. So we're getting there. We're going to continue with Moore's Circle, hopefully finish that up today, and then we're going to jump into start a review of what you I'm assuming. Do you guys have Chris Allen for statics? Hopefully Chris went through this with you, okay? What we're going to go through next with respect to beams, just a little refresher as we get into beam bending and moments and shears and shear lag and shear transfer and things like that and stresses. So hopefully get everybody on the same page. But we're going to finish up Moore's Circle. So you have homework due on Friday. It's all about Moore's Circle, right? So I need to quiz you on Moore's Circle. That's going to be quiz number 6. It seems not cool to give you a quiz that's due on Sunday when the homework's due on Friday. Are you anybody opposed to me opening up the quiz for, say, through Monday? Or are you guys just going to procrastinate anyway? It's going to do it Monday no matter what. All right, so here, I'm going to open it up. It'll be open noon on Friday through Monday at midnight, okay? Yes.
Does it tell you when someone takes the quiz?
It tells me if they're in progress or they have completed it, not like the time in which, and it gives me the time you guys were in it, working through each problem, but I don't think it gives me the actual time in which you took it. So, again, take your time, okay? There are quite a few of you that take most of the time, and I think overall, time is an indicator of how well someone does on the quiz, okay? So I know 2 hours is a lot to set aside, but I think it does help, okay? Okay. Anything else? Nope. All right, so Moore's Circle. We talked about this idea of max in plane versus absolute shear stress and the difference between it too, right? I had my box, which someone thought was garbage and they threw it away, I guess. Right, but we live in a 3D world and there are real stresses. Oh shit, there it is. And it's kind of like slants a little bit. Right, 3D world, we got this stress block. Okay, we assume plane stress. So we're only looking at these 4 sides, right, of our 6-sided cube. Well, in reality, we've got 6 sides to this cube, and even though we start by saying we have no stress on the front and back, right, the z faces of this cube, the fact that we have 0 stress on the z faces of this cube actually results in a Moore's Circle, right, for all 3 of our stress blocks, right, the xz, yz, and the xy, and plotting all of them together, we actually can get situations and conditions where we have even larger shear stress, right? So if our principal stresses or our xy plane created this black circle here, right? Once we consider the fact that we're in plane stress and we have this 0 normal stress acting on the faces that are facing us, we get a principal stress here at the origin, and so we end up with this larger circle, which creates a larger absolute shear stress, okay? We just want to keep that in mind. Okay, so we're going to do a couple more examples. Okay, I think examples are key on this concept. So we have a point in a structural member subjected to plane stress. We know that that is a very reasonable assumption to make. We've already gone through, or someone has gone through, and established what the stress is acting on the horizontal and vertical planes of this element, right? Oriented as shown. and they want us to draw the Mohr's circle for this stress state, essentially plotting our points, drawing the circle, finding the center, finding the radius, right? We've done all of those things already. You're doing that in the homework. We want to determine the principal stresses and the maximum in-plane shear stress acting at the point, and we want to illustrate that at the element, on an element that's rotated at that angle, right? Because we know that these aren't the principal stresses, because if this were the principal stresses, we'd have no shear stress, right? So we're going to have to rotate this some amount in order to get to the maximum points on our x-axis, right? Sigma 1 and sigma 2. They also want us to determine the normal and shear stresses at the plane indicated. So they said, all right, well, we want to know what's going on this plane. So what normal stresses and shear stresses are acting on a cube that's oriented parallel to this plane, right? A four to five triangle here. Then they want us to draw that on a sketch. And then lastly, they want to determine the absolute maximum shear stress at the point, right? Absolute maximum. So we want to make sure that we consider the fact that we have normal stresses in the z direction of 0, and that may affect our Mohr's circle, right? And our absolute maximum shear stress. But sometimes our in-plane stress, right, it can be maximum. In-plane stress is maximum when either our principal stress in the y side is 0 or it's negative, right? Essentially, if we encapsulate this origin point within our in-plane circle, then that means our two circles are actually inside our xy circle. So our maximum absolute shear stress is our maximum in-plane shear stress, right? Those two are the same. Okay. I'm gonna do this. I wasn't gonna give this to you, but I'm gonna give it to you. Because I'm being lazy and we need to move forward. Okay, so in this example, here is Mohr's circle, right? I was going to draw it out, but we need to move ahead. So if we had, so this is 3 pages down on the skeleton notes. This is a computer-generated Mohr's circle, okay? So we have the indicated stresses on our stress block, right? So on the X face, we have 3.8 KSI in compression and 5.7 KSI in shear. So if we were to plot those points, right, we have compression, well, that is on the left side. Right, this is our normal stress. To the right is positive, positive being tension, right? We also know that shear stress, we consider downward positive, or at least that's the way the axis is drawn, with a counterclockwise shear stress being on the bottom side of the x-axis. We have a clockwise shear stress being on the upper side of the x-axis, okay? So based on that sign convention, 3.8 KSI in compression, 5.7 KSI in shear. It's counterclockwise, right? The shear here is counterclockwise. So this is our point, right? So that's our X face point. We would plot this on our diagram or grid or graph. Then we need to plot our Y point. Well, it's 9.4 KSI and 5.7. In this case, it's clockwise for our shear stress and tension for our normal stress. So we're way up over here, right? Now that we have both of those points, we're going to be really interested in a couple things, right? We want to know what the radius is. If we know what the radius is, that helps us provide a point, right, or a known stress state at any point around this circle. We also want to know what the center is, right? So that also is a critical point to help us figure out all of the points surrounding Mohr's circle. It seems kind of busy here, but we have our 2 additional circles, right? We have a plane stress state, so we're looking at the XY faces, right? Coordinate X, coordinate Y. Well, on our Z face, if we were looking at the XZ or YZ plane here, right? The Z face would have 0 stress in it, and so we decided that that meant that our principal stress, our third principal stress, rests at the origin. So in this case, if we were to draw a Morse circle for the XZ axis, we would get points on the x-axis that are sigma 1, or our first principal stress, and sigma 3, which is our principal stress in the z direction. We would draw a circle. If we did that for the YZ plane, we'd get a smaller circle that went between our second and third principal stresses, right? So as you can tell, as I mentioned, sometimes our in-plane shear stress and our absolute maximum shear stress can be the same thing, and in this case it is, because our third principal stress, or our 0 sigma z, lands within our Morse circle, right? Our Morse circle for in-plane, which is our xy. Does that make sense? So if we wanted to know what the radius is, I'm going to jump back up here, just so I didn't have to draw it and you guys didn't either. We know the radius is our x normal stress minus the y normal stress squared, or over 2 squared, plus shear stress squared. In this case, 8.72 KSI, right? Pretty easy, plug it in, right? Negative 3.8. Make sure we maintain our signs. Negative 8, 3.8, because it's compression. Minus 5.7 divided by 2 squared, plus our 5.7 squared. Or sorry, 9.4. So we get a radius of 8.72, as I mentioned. Always good to know what the center is. Well, the center is our average stress. That is sigma x plus sigma y over 2, or negative 3.8, following the sign convention, plus 9.4 over 2. We get a center point of 2.8 KSI. So if we go back down to our drawing here, right, the radius in our case is 8.72 KSI. And the center point, right, it just has coordinates. The coordinates are the average stress, comma 0, right? Average stress being 2.8 KSI, comma 0 KSI, right? 0 shear stress, the center is always going to be where it crosses the x-axis, so we have 0 shear stress. So 2.8 comma 0, that's our coordinate for the center. And that would be our Morse circle, right? So that would be the answer to problem 1. So now they wanted us to determine the principal stresses and the maximum in-plane shear stress acting at the point and illustrate that on a little diagram. Well, if we do, let's go back up here. We'll call this A, and we'll say C. All right. So if we want to know what the principal stresses are, we know the principal stresses are where we have 0 shear stress, right? So we're trying to get to where the circle intersects the x-axis on either side. So in this case, whoops. P1 is going to be sigma max. We have the center plus the radius. Well, that's 2.8 we decided was our center. Plus the radius was 8.72. We get sigma max equal to 11.52 KSI. And then our minimum stress, or our principal stress, sigma P2, is the center minus the radius, or 2.8 minus 8.72, or negative 5.92 KSI. They also asked us for the maximum in-plane shear stress, right? So that is the top and bottom of our circle. Well, in that case, we know that that magnitude is just the radius, right? So our maximum shear stress equals the radius equals 8.72 KSI. Then they asked us to illustrate an element with a rotation angle at the principal stresses. Well, if we start by looking at a stress block, right? So we have our initial stress block or stress state. We had our shear stresses. Normal stresses on the Y face were in tension. X face was compression. Well, if we go back to our Moore's circle, right, this was our initial stress state. Well, to get to our principal stresses, right, we could either rotate all the way around this way or rotate back this way, right? If we rotate all the way around this way, the principal stresses are just going to act at 90 degrees to one another from being the other way, right? It's just which face they're oriented to. So I'm going to rotate this Y back down to the x-axis. I'm going to transform our Y face into this sigma P1, right, which is our maximum normal stress. So I really need to know what that angle is. Right, if we called this angle alpha, alpha P for the principal axis rotation. There we go. All right, so we need to know what alpha P equals. Well, alpha P equals the inverse tangent of the opposite over adjacent, right? Well, if we go back and look at our inverse tangent, all right, this will be opposite over adjacent. So we need to know what the magnitude that the Y point is above the x-axis. Well, that's easy. That's our initial shear stress, right? The adjacent, well, that's the normal stress that's beyond the center, right? So we would essentially need to grab this coordinate, which is 9.4, minus the center coordinate, which is 2.8, and that'll give us our adjacent, right? And then we can do our inverse tangent. Going the wrong way. So we know that this is the tangent, inverse tangent, sorry, of 5.7 over 9.4. That's our y. That's our coordinate of our y point. Minus, we know we have to take away the center in order to get that amount, right? That adjacent leg. If we do that, we get a sigma p or alpha p of 40.8 degrees. We also know that that's in Moore's circle world, right? Moore's circle world is twice that of the real world. So if we rotate 40.8 degrees on Moore's circle, we really rotate 2 times the real world. So theta now equals 20.4 degrees. So this stress block, as we see now, in order to figure out what the surfaces are, like the planes in which we get our principal stresses, we need to rotate this block 20.4 degrees. And then the sides of that rotated block are going to have our principal stresses, right? The maximum normal stresses we're going to see in our block. So I will just draw a line like that. Right, this is 20.4 degrees. because I rotated down. There's my stress block. Those are my axes, right? We had a Y face and an X face, like we had in our normal block. Now those have rotated down, as you can see there. Well, now if we look back at our circle, it's our Y face that's going to have our maximum tension stress, right? And our X face, which is going to have our maximum or minimum stress, which is actually a negative stress. So I just want to make sure that I populate the stress block right. So the X face should actually be negative. What does that mean? That means it's in compression. So 5.92 KSI. And then our Y face, well, that's our sigma 1 or our maximum principal stress, which we decided was 11.52 KSI. And that's part B. Right? We figured out the maximum in-plane shear stress, 8.72. We figured out what the maximum principal stresses were, and we drew a block that indicated the planes in which those stresses act. Right? So if we took whatever material this was at, and we say we sliced it at a 20.4 degree angle, we know that that face was going, this face here would have 5.92 KSI in compression. It'd be the worst case compression stress. If we sliced it the 90 degrees from that, we would get the worst case tension stress, right? Or the maximum stress. All right. Part C, we asked, they were specific in asking us to look at what are the stresses, the normal stress and shear stresses on the indicated plane, and show them on a sketch. So obviously, in the real world, you would be able to analyze an existing condition, right? Like we've done before with external forces. We got shear stresses for a stress state. Now, obviously, there's a plane of interest in this material or this element that they want us to know what are the stresses acting on that plane. Maybe there's a connection that's oriented, in a 4 to 5 triangle. Maybe there's a weld that's welding two pieces of steel together at this angle. Right? And we want to know exactly what the stresses are acting across that joint so we could just design that or at least check its capacity. Well, first thing we want to know is, well, what is that orientation? What is that theta, right? We have an orientation here. We want to know what's the new orientation that we're trying to figure out these stresses. So theta, a lot of inverse tangent here. I know you guys love trigonometry here. In order to get that angle, we could use the inverse tangent, opposite over adjacent. Right? Opposite being 4, adjacent being 5. We can figure out what that angle is at 38.66 degrees. Okay. Well, knowing that we're now going to be rotating this counterclockwise, 38.66 degrees, right? This is where we can go back to Moore's circle that we've already established for our known stress state, right? We've got our 2 points. And we know that now we need to rotate it 38 degrees about to the left to figure out the 2 new points, right? Because these are going to be our stress states on the X and Y face, right? Or this face and then a face perpendicular to it of that element. So we're going to rotate and call that alpha 1. Well, if theta was 38.66 degrees, right? We know that alpha 1 equals 2 times theta, right? If in the real world we're going to move 38.66 degrees, on Moore's circle we got to rotate twice that, right? So we need to take 2 times theta, or 2 times 38.66. We get 77.32 degrees. So alpha 1, right, how far we're going to rotate, is 77.32 degrees. Right? Yeah. Well, if we know alpha 1 is 71.32 degrees, we really want to find these legs of our triangle, right? We're trying to find coordinates on this circle. Well, we know the radius. We know the radius, and we knew this angle here. These coordinates would be really easy, right? Sine and cosine of that angle times the radius. So in order to get this, based on word circle, well, we could say, we know that the principal angle, we've already established that. We've already established that we're trying to do this 4-5 triangle, right, which was 77.32 degrees. And we know from x-axis around to x-axis is 180 degrees. So this angle, we're going to call it beta. Well, that equals 180 minus alpha 1 minus our principal angle, right? Our principal angle we know was 40.8 degrees. And we know alpha 1 is 77.32 degrees. So beta now equals 61.88 degrees. And the rest of it just pops right out, right? Now that we know the radius, we know what that angle is. We know what those coordinates are. So we got our y, right? This is y. This would be x. Our y equals r sine of theta. 8.72 sine 61.88. We get 7.69. Okay, that's our y, 67.69 KSI. Our x, our cosine theta. Well, if we plug that in, it's 4.11 KSI. These are our legs, right? Well, our actual coordinate is going to be the center coordinate minus, or this leg minus the center coordinate, right? Because we're actually past the origin. We're passing through the origin to the center. We're figured out what distance is from the center to our point of interest. So really, right, this being our normal stress, that equals x minus the center, or 4.11 minus 2.8 equals 1.31 KSI. Because we're on the left-hand side of our y-axis, we're negative meaning we're in compression, right? So the 1.31 KSI is in compression. Again, these magnitudes are equal on the other side, right? So we get same thing going on. We have 7.69 for our y, 4.11 for our x. If that's the case, this coordinate now becomes 6.91 KSI, comma 7.69 KSI. This coordinate is, right, as I mentioned, negative 1.31 KSI, comma, negative 7.69 KSI. That makes sense how messy I made that? Going deep. I don't know.
We'll talk about this.
Yeah, it'd be 4.11 plus 2.8. Because we figured out what is the leg from the center. The center is already a distance from the origin, so you add 2.8 plus 4.11, you get 6.91. And then your vertical leg stays the same, right? Because you're really, the center is at the x-axis. All right, we're not done yet. We got to take those values, and they asked us to put it on a sketch. So we're going to go back up here, and we're going to start by saying, okay, part C, they want to determine the normal and shear stresses on the plane, show these stresses on a sketch. Well, we know based on this little rendition, right? We're rotating counterclockwise 38.66 degrees, right? So we're going to take this block, we're going to rotate it that far to the left. So I'm going to just, oh, I keep going the wrong way. I'm going to do something like this. I'm going to say that this is theta, which is 38.66 degrees, right? This is the rotation that we've decided we want to orient one of the sides of this stress block, right? So we can figure out what the stresses are via Moore's circle and transforming the stresses. So now our block is going to sit something like that. Well, our sides are still oriented like they were, right? So this is our X face, this is our Y face. If we rotate it counterclockwise to the left, right? This is our X face, that's our Y face. We're going to maintain that. Right, so this is X, this is Y. So based on that, right? We took the Y and rotated it. So if we start by looking at the Y face rotated over, and now we have the Y face in compression, 1.31 KSI, and then a clockwise shear stress. Keep going down. I don't know what my problem is. Clockwise shear stress, we know it's in compression, right? It's 1.31 KSI of compressive stress to be exact. And then on the other side, we rotated, we took the X face, which was originally in compression, right? 3.8. It rotated down past the Y-axis, so now it actually started getting into tension all the way up to our rotated point. So now we're in tension. We get 6.91 KSI, and our shear stress, right? Tau XY and tau YX are the same, equal and opposite. We get 7.69 KSI. All right, last part of this example. They asked us for the maximum, or determine the absolute maximum shear stress. Well, we know based on this Moore's circle, right? If we were to draw in our two additional circles based on our principal stresses, right? Sigma 1, sigma 2, and sigma 3. Based on doing that, our XZ and our YZ blocks land within our XY block, circle, right? Moore's circle. So this is truly the ultimate shear stress, both the maximum in plane, but also the absolute maximum shear stress that you would see in an element. So you could say tau max in plane equals tau max absolute equals the radius, which is 8.72 KSI. Right? What's that?
Is that what you need?
No, so that's what I'm saying as we went through before on Friday, is that if you have this condition where you went through and we plotted our 2 points, okay? We drew our Moore's circle for our stress state, and we were off to one side of the x-axis. or the y-axis, sorry, the origin, right? If your 2 points are either, or your 2 principal stresses are either both in tension or both in compression for your in-plane Mohr circle, then that means your principal stress in the z direction is outside your circle. And if it's outside your circle, that means when you draw a circle from that principal stress to your other 2 principal stresses, you're going to get a larger circle, right? And because you get a larger circle, that absolute maximum shear stress is going to be greater than the in-plane shear stress. They can either be equal or the absolute's going to be greater. In our case here, they were equal because our initial stress state, okay, was on either side of our origin, right? You had a tension and compressive stress. If you do that, then this 3rd point is in the middle of your circle. All right, more examples. Damn, gotta get moving. All right. This is very similar to the homework, okay? Where we're actually given a Mohr circle for a point in an object. It's undergoing plane stress. They want us to determine what are the stresses and show them on a stress element. And then they say, determine the principal stresses and the maximum in-plane shear stress acting at the point and show these stresses on an appropriate sketch. Well, that's easy. If we wanted to establish what the stress state is, we just need to know these coordinates, right? Coordinates of x face and y face, they're already labeled as their x point and y point. They gave us the scale here, which also in the homework, give you the scale. So 1 grid in this case was grid square is 10 megapascals. So you just count them up, right? So we count them up and we want to establish what our coordinates are. So if we establish our coordinates, all right. Our x face is going to have a coordinate of 80, comma 70. Y face is going to have negative 20, comma 70, right? And I guess this bottom being positive is technically in order to get a legitimate coordinate would be negative 70. So those would be the stresses at each of those faces. So based on that, knowing Mohr's circle, right? Counterclockwise shear on the bottom end, clockwise above the x-axis. Normal stress is positive or in tension on the right-hand side of our y-axis. They want us just to draw this stress state, right? So we draw a stress block. We know that our x face, right? If we drew it, this was x, this was y. Okay, our x face we know is 80, 70, so 80 megapascals of normal stress, positive being tension. So we're going to say we have 80 megapascals. We have 70 counterclockwise megapascals for our shear stress. Well, if that's counterclockwise, we know that on the y face it's got to be equal and opposite. So it's clockwise 70 megapascals. We also know that the coordinate for our y point was negative 20. Negative 20 meaning compression. So we have 20 megapascals in compression. So if we're given Mohr's circle, right, and 2 points, given our initial stress state, we can come back and back out what that initial stress state looks like, right? So that's part A. That's easy enough. Part B, determine the principal stresses and the maximum in-plane shear stress acting at the point and show these stresses on an appropriate sketch. Okay. As I've been mentioning over and over again, the principal stresses and the maximum shear stress, those are the important ones, right? Those are what we're going to relate back to our material properties. So someone's going to give us what the failure stress is, right? The point at which our material is either going to yield or it's going to physically break, okay? Then we add some factor safety to it, so we reduce those numbers to an allowable stress, and then we relate that allowable stress to the maximum stress that our element's going to see, right? And so if we were to just look at this initial stress state, we would know that we might have, say, an allowable stress. These might be within our allowable stresses, but when we go and look at our principal stresses, which are likely going to be larger, they might not be. So again, in order to find our stress state, our principal stresses, we need center and radius, right? Those are the big ones. That's our average stress. In this case, it's 30 megapascals. You could also scale it off of that if you really wanted to. Radius, 86 megapascals, right? Square root is sum of the squares. Maximum in-plane shear stress. Well, we know that equals our radius. Well, that's 86 megapascals. Well, that was easy. Our principal stresses, those are pretty easy too, right? Our maximum stress, or our sigma P1, is really our center plus the radius. Well, that's 116 megapascals. Our second principal stress, which is our minimum stress in plane, is C minus R, right? Or negative 56 megapascals in this case. We also need to know what this angle of rotation is, right? Because we need to know what the orientation is so that we can draw it on a stress block. So we need to know what alpha is. Well, we're all going to get really good at the inverse tangent, right? Adjacent over opposite, opposite over adjacent. Woo! I'm going to get good at it too, I promise. All right, so opposite over adjacent. In that case, we've got tangent inverse opposite over adjacent equals the inverse tangent of 70 over 80 minus 30, right? We essentially took our x coordinate, the vertical leg, well, that's just our shear coordinate or our y coordinate. The horizontal leg, well, that's our total coordinate minus the center coordinate, right? Because 80 comes from the origin. Well, we need to come from the center in order to get our adjacent leg. So we get our adjacent leg. This all equals alpha. Well, alpha equals 54.46 degrees. We know that there's a difference between the real world and Mohr circle world, right? So we got to divide that angle by 2 to get what the orientation of the actual stress block is. So we end up with this sketch. This sketch is important for the homework, because I referenced this example in the homework, okay? This is a sketch that I'm looking for in the homework. Okay. So we were given an initial stress state. Right? We backed it out based on this graph, but we could have been given this initial stress state. And then a depiction of what our maximum shear stress is and our maximum principal stresses are, right? Or our principal stresses, which are essentially maximum. We can draw it like we see it here. So we just determined that our theta angle was 27.23 degrees counterclockwise. Okay? So we take our initial orientation. We have our initial x-axis. We need to rotate it. The angle we determined, right, was oriented to the principal stresses. So I did that, or the computer looked at that, right? Then we orient our block on that angle, okay? And we know that on our X face, in this case, we have a maximum principal stress of 116 megapascals in tension. We have 56 in compression, right, on our two faces. Well, in order to depict the maximum shear stress, well, the maximum shear stress acts at 90 degrees to our principal stresses, right? Principal stresses are along our x-axis. Maximum shear stresses are along our y-axis, right, or a line that is parallel to our y-axis. Well, the difference between those two lines is 90 degrees. In the real world, that's 45 degrees. So what we can do is in order to depict both of the principal stresses and the stresses acting when we have our maximum shear stress, we can just cut a line at 45 through that stress block. And on that face, you're going to get your maximum shear stress and whatever associated normal stress, right? Yeah.
So to get your radius, why can't you just do Pythagorean's theorem on your CX line with the 80 and 70? Just find the length of that line from C to X using your coordinates 80 and 70.
It would be different, right? Because you would be effectively trying to find, you'd be taking this leg. Nope, sorry. This leg and this leg,
Oh.
right? Longer.
Yeah.
The adjacent leg is the one that you'd be missing. You'd make it longer so your theta would be up.
Okay. I see that now.
Okay. Any questions there of how to draw that or why that works? Right? We essentially rotated the 27 to get to our principal axis or principal stresses, and then we rotated another 45, right, which was 90. So this is 45. And if we rotate another 45, right, which is 90 on here, we rotate up, and then we rotate up, right, to this point here. Whoa. I'm not going to do that. So we rotate up, and then we rotate up. And when we do that, we end up with that 30 of normal stress, and then our shear stress, right? All right, we're getting so close to being done with Moore's circle. A couple more things. We're going to go through one more. All right, one more. And then I'm going to apply it to an actual stress situation, okay? So consider a point in a structural member, plane stress, it's given. We want to draw Moore's circle for this. So we got our coordinates. Counterclockwise, clockwise, positive, normal stress, shear stress. In this case, right, we have our X face and our Y face for our stress state. 25 megapascals of shear, 45 megapascals on the Y face of compressive stress. We know already that our X point is going to be on the Y axis, right? So if we were to plot that point, we might be somewhere up here. This is 0, negative 25, right? Because it's clockwise. The shear stress on the X face is clockwise. We know we're going to be equal and opposite on the bottom end, but in this case, we're going to have a compressive stress of 45. So I'm going to set this thing right here. I'm going to draw a line between them. I'm going to draw a circle around them. Something like that. So we have our X face, we plotted our Y face, same concept. Y though, right? We had negative 45 comma 25. That would be our coordinate based on the sign convention of the Morse circle. We know here, again, our absolute maximum shear stress is going to be the same as our in-plane maximum shear stress because this zero origin point lies within our circle. As mentioned, big players here are the center, which is our average stress. In this case, it's negative 22.5 megapascals. Radius, another big player, right? In this case, it's 33.63 megapascals. Center. So we've got negative 22.5 comma 0. Obviously, you guys don't want to stick around. All right. I'll see you guys Wednesday. Don't forget, homework due Friday.